Somewhere in Shenzhen, inside a facility most of the world has never heard of, a machine switched on in December 2025 that wasn't supposed to exist. Not this decade. Not according to the company that spent 30 years and tens of billions of dollars proving nobody else could build it. That company is ASML, based in the quiet Dutch town of Veldhoven, and for 2 decades it has held something close to a technological monopoly, the only maker on Earth of the machines capable of printing the world's most advanced computer chips. Then, according to a Reuters report that first surfaced the story, a state-backed consortium coordinated by Huawei approved the operation of a functional prototype extreme ultraviolet lithography system. The people who spent years insisting this couldn't be done anytime soon are now the ones scrambling to figure out exactly how far behind they actually are. To understand why this matters, you have to understand what ASML's monopoly was actually built on, because it isn't simply they make good machines. It's a single, almost absurdly difficult engineering problem that the rest of the semiconductor industry spent decades treating as effectively solved and permanently exclusive. Every advanced chip starts with the same basic process: shining light through a stencil onto a silicon wafer, similar to shining a flashlight through a cutout to project a shape onto a wall. The smaller the wavelength of that light, the smaller the features you can carve into a chip. The most advanced chips today require light with a wavelength of 5 nanometers, a band called extreme ultraviolet, or EUV. Here's the problem: light that short does not exist anywhere in usable form in nature. You cannot buy an EUV bulb. It has to be manufactured instant by instant inside the machine itself, and doing that turned out to be one of the hardest engineering problems humanity has ever solved. ASML's solution, refined over 3 decades, works like this. A machine fires molten droplets of tin, each about the width of a grain of sand, into a vacuum chamber at roughly 70 meters per second. As each droplet falls, a high-powered laser strikes it twice, first flattening it into a pancake shape, then blasting it into a plasma reaching temperatures hotter than the surface of the sun. In that instant, the dying tin releases a flash of 5 nanometer light. Then the whole sequence repeats 50,000 times every second for months on end without missing a beat. Back in the 1980s, plenty of serious scientists considered EUV lithography simply impossible. It took roughly 30 years and tens of billions of dollars to prove them wrong. And that 3-decade head start is precisely the gap the rest of the world has been trying to close ever since. The result of that head start is a monopoly almost without precedent in modern industry. ASML is the only company on the planet that manufactures EUV lithography machines. There is no second supplier anywhere. A standard machine costs upward of $200 million. The newest, most advanced models with expanded optics run closer to $380 million apiece for a single tool. Every leading-edge chip in the world, whether it ends up in a smartphone or an AI data center, has to pass through a machine built by ASML at some point in its production. There is no other door. That position pushed ASML's market value past $670 billion, a record for a European company, and gave the firm, and by extension the governments of the Netherlands and the United States, which jointly control what ASML is permitted to export and to whom, genuine geopolitical leverage over the entire global technology industry. That monopoly isn't just a matter of ASML alone guarding a single secret formula, either. Part of what makes the company so difficult to replicate is that it doesn't actually build most of the individual components inside its own machines. It functions more like the conductor of a vast, tightly coordinated global orchestra of specialized suppliers, each contributing a piece of the puzzle that no single company outside that network could easily reproduce on its own. The precision lasers that vaporize each tin droplet come from Trumpf, a German optics and laser manufacturer. The mirrors used to direct the resulting EUV light through the machine come from Zeiss, another German firm, producing surfaces so flat and precisely polished that they rank among the smoothest man-made objects on Earth. Because EUV light is absorbed by almost everything, including ordinary glass and even air, meaning the entire internal light path has to rely on mirrors rather than conventional lenses. The plasma generation technology at the heart of the tin droplet system traces back to a California-based company called Cymer, which ASML acquired outright in 2013, specifically to bring that piece of the puzzle in-house. What ASML actually owns, more than any single component, is the accumulated knowledge of how to make all of these individually difficult pieces function together in perfect synchronization, thousands of times a second, for months at a stretch, without catastrophic failure. That kind of integrated systems knowledge, built up over decades of iterative engineering and quietly accumulated inside a small number of specialist firms, is precisely the sort of asset that's almost impossible to shortcut, buy, or steal your way past. Which is exactly why so much of the commentary around China's progress has focused less on any single breakthrough and more on the years of patient, incremental effort still required to build an equivalent ecosystem from scratch. That leverage is precisely what Washington and its allies have used against China for the better part of a decade. Export controls put in place across multiple U.S. administrations have specifically barred ASML from selling its EUV machines to Chinese customers, on the theory that if China can't buy the tool, it can't make the chip, full stop. The strategy rested on one central assumption, repeated confidently and often by ASML's own leadership, that the technology gap was simply too vast to close through indigenous effort alone. Christophe Fouquet, ASML's current chief executive, said as recently as April 2025 that China would need many, many years to develop EUV technology competitively. His predecessor, Peter Wennink, was characteristically blunter, once describing the gap in an interview as China being light years behind. Light years. As of 2024, Fouquet was placing the number at somewhere between 10 and 15 years, a timeline suggesting China's own domestic EUV capability, if it arrived at all, wouldn't be a near-term concern for anyone. That confidence is exactly what makes the Shenzhen news so significant, and exactly why so much of the coverage since December has framed it in stark, almost incredulous terms. The prototype, developed through a partnership between Huawei and Shenzhen Skycarrier, a company that has become one of the central pillars of China's push toward semiconductor self-sufficiency, was validated in late 2025 and is now reportedly targeting commercial-grade deployment on fab floors by 2028. Unlike the tin droplet laser-produced plasma approach that defines every ASML machine, the Chinese system uses a fundamentally different mechanism called laser-induced discharge plasma, or LDP. Rather than blasting tin droplets with lasers in a vacuum chamber, LDP generates the same 5 nanometer EUV light by vaporizing tin between two electrodes and converting it into plasma through a high-voltage electrical discharge, letting electron-ion collisions produce the required wavelength directly. Proponents of the approach argue it offers a simpler architecture, a smaller physical footprint, and potentially better energy efficiency than ASML's method, though crucially, it remains unproven at the scale and reliability required for actual high-volume chip manufacturing. And that gap between it works in a lab and it works on a production line making millions of chips with almost no defects is where the real story gets more complicated than a simple headline suggests. Independent analysts who've examined what's actually been demonstrated in Shenzhen paint a considerably more cautious picture than the framing of China just matched ASML would imply. The light source in China's current prototype produces somewhere between 100 and 150 watts of usable EUV power. For comparison, ASML's light source reached 250 watts back in 2017, sufficient to produce 125 wafers per hour, and the company's current commercial benchmark sits at roughly 600 watts, with a 1,000 watt system announced in early 2026 research. In practical terms, that wattage gap directly translates into throughput and yield. The general industry rule of thumb holds that you need roughly 250 watts to make usable 7 nanometer chips, 350 watts for 5 nanometer, 500 watts for 3 nanometer, and a full kilowatt to reliably produce 2 nanometer chips, the cutting edge currently used in flagship smartphone and AI processors. At 100 to 150 watts, China's prototype is nowhere near the power level required to compete with what TSMC, Samsung, or Intel are currently shipping. And beyond the raw wattage gap, the Chinese system also reportedly loses a larger share of its energy to heat and off-target wavelengths instead of producing usable 13. 5 nanometer light, a sign of a less mature, less refined engineering process, still working through problems ASML solved years ago. One of the more revealing details to emerge from reporting on the project concerns exactly how China closed even this much of the gap. According to sources close to China's government-backed EUV program, cited in independent analysis of the prototype's development, the breakthrough would have been nearly impossible without the intimate knowledge of former ASML employees who had since joined Chinese semiconductor efforts. That detail matters enormously for understanding what actually happened here. This wasn't a case of Chinese engineers independently rediscovering 30 years of accumulated, painstakingly earned optical and plasma physics knowledge from first principles in a few short years. It was, at least in significant part, a case of specialized human expertise, the kind of tacit, hard-to-document knowledge that lives in the heads of engineers who spent careers inside ASML's own supply chain, migrating to a new employer and a new national project. ASML has long understood talent flow as one of its most difficult vulnerabilities to defend against. You can restrict which components get shipped and to whom, but restricting where an engineer chooses to work next is a far harder problem, and one export controls were never designed to fully solve. Beyond the lithography machine itself, the Shenzhen prototype sits within a much broader Chinese push toward full semiconductor equipment self-sufficiency. one that's been advancing on multiple fronts simultaneously rather than depending on any single breakthrough. Chinese chipmakers have already made substantial progress on less advanced but still critical tools. ASML, the country's largest contract chipmaker, has been testing a domestically produced deep ultraviolet lithography machine built by a Shanghai-based startup called Yuliangsheng, aimed at reducing reliance on ASML for older, less advanced chip nodes, even while the EUV gap remains unresolved. Industry trackers estimate China has pushed its overall semiconductor equipment self-sufficiency to roughly 35% as of early 2026, with particular strength in areas like thin film deposition tools and ion implanters. Unglamorous, but essential pieces of the overall chip-making process that don't generate headlines the way EUV lithography does, but that collectively reduce the number of remaining single points of failure in China's domestic supply chain. Viewed against that backdrop, the Shenzhen EUV prototype isn't an isolated moonshot. It's the most prominent, most closely watched piece of a much larger, multi-year industrial strategy that's been advancing steadily across dozens of separate toolmaking categories at once. Separately from the Shenzhen LDP prototype, researchers at Tsinghua University have spent years developing an entirely different approach called steady-state microbunching, or SSMB, a particle accelerator-based method that generates EUV light by circulating electrons at nearly the speed of light around a storage ring and using a precisely tuned laser to compress them into microscopic, evenly spaced bunches that radiate coherent light almost like a continuous laser rather than a strobe. The foundational proof of concept for SSMB was actually published back in February 2021 in a paper appearing in Nature, based on experiments conducted not in China, but at a synchrotron facility in Berlin, in partnership with Germany's Helmholtz-Zentrum Berlin and the Physikalische Technische Bundesanstalt Metrology Institute. Chinese media nicknamed the eventual production version of this concept the lithographic cannon, and the theoretical power ceiling is genuinely impressive on paper, potentially exceeding a full kilowatt of EUV output, and in principle capable of feeding multiple lithography stations from a single shared accelerator, a fundamentally different economic model from ASML's one machine, one price tag approach. But SSMB, however promising the physics, remains considerably further from commercial reality than the Shenzhen prototype. The Tsinghua project has reportedly secured funding for a dedicated test site in Chongqing, with a planned accelerator ring stretching somewhere between 100 and 150 meters in circumference. A genuine national infrastructure undertaking, not something built on an assembly line. Independent analysts tracking China's broader lithography ambitions describe the SSMB effort as still in early stages, a wild card that could eventually redefine the industry, but that hasn't yet produced anything resembling a working lithography tool, let alone a commercially viable one. The 2021 Berlin experiment proved the underlying physical mechanism functions as theorized. It did not, and does not, constitute a chip printing machine. Confusing that lab-scale proof of concept with an operational EUV source, a mistake that's shown up repeatedly in viral social media coverage of the SSMB story, significantly overstates how close China actually is on that particular technological path, even as the Shenzhen LDP prototype makes real, if still limited, progress on a separate one. What makes the current moment genuinely different from the endless cycle of China closing the chip gap headlines that have circulated for years is the shift from rumor and leaked photographs to something closer to institutional confirmation. Earlier reporting, dating back to March 2025, described Huawei testing early EUV-related components at its Dongguan facility based on photographs posted by sources on social media, without any official confirmation attached. By comparison, the December 2025 development represents a formal, institutionally acknowledged milestone, a state-backed consortium's approval of prototype operation, reported by a major international wire service, discussed openly in subsequent Chinese and international industry analysis. That's a meaningfully higher evidentiary bar than photographs of undated equipment circulating on social media, even if the underlying technological gap to full commercial viability remains substantial. Financial markets registered their own verdict on the Shenzhen news, though in a more measured way than the geopolitical rhetoric surrounding it might suggest. ASML's share price saw only modest movement in the trading sessions immediately following the Reuters report, reflecting a market view that treated the prototype as a meaningful long-term development rather than an immediate threat to the company's near-term revenue, the vast majority of which continues to come from customers with no legal ability to purchase Chinese-made alternatives, even if those alternatives were commercially viable today. Analysts covering the semiconductor equipment sector generally characterize the news as raising the probability of eventual competition somewhere in the 2030s, rather than changing any near-term earnings forecasts, with several noting that ASML's roughly $300 billion order backlog, built almost entirely from customers in Taiwan, South Korea, the United States, and Europe, remains effectively insulated from Chinese domestic competition for the foreseeable future, given existing export restrictions on where those customers' own products can be sold. That muted market reaction stands in notable contrast to the far more dramatic tone of much of the surrounding media coverage, illustrating the gap between how professional industry analysts assess incremental technical progress and how that same progress tends to get amplified once it reaches broader public discourse. The response from ASML's three primary customers, TSMC, Samsung, and Intel, has been similarly measured, at least in public statements, though each company has its own distinct stake in how this story eventually unfolds. TSMC, which manufactures the overwhelming majority of the world's most advanced chips and depends entirely on ASML's EUV tools to do so, has publicly maintained that near-term supply chain risk from Chinese domestic EUV progress remains minimal, given the years-long gap between prototype validation and commercial-scale production reliability. Samsung, competing directly with TSMC for advanced foundry business, has occasionally used China's slow but real progress as a data point in broader conversations about diversifying its own supply chain risk, without suggesting any near-term change to its own ASML-dependent manufacturing roadmap. Intel, meanwhile, sits in a somewhat different position. The company has spent recent years attempting to rebuild its own advanced manufacturing capability after falling behind both TSMC and Samsung, and some industry observers have noted that a longer-term erosion of ASML's absolute monopoly, even one still years away, could theoretically benefit Intel's manufacturing ambitions by eventually introducing pricing competition into a market that has, for 2 decades, had none. In the months following the Shenzhen revelation, the confrontation over China's EUV progress escalated into a more pointed diplomatic dispute. U.S. Commerce Secretary Howard Lutnick reportedly told ASML directly that one of the company's 180-ton EUV machines may have somehow reached China despite export controls, an accusation ASML firmly denied, with the company stating it has never shipped an EUV machine, nor any specially designed component for one, into the Chinese market. ASML's response leaned on the kind of granular tracking most manufacturers can't claim. The company said it monitors all of the roughly 314 EUV machines it has ever produced through remote telemetry, tracking their operational status and physical location continuously, and that its contracts with customers explicitly prohibit removing, transporting, or relocating an EUV system without ASML's direct involvement. Whatever the resolution of that specific allegation, the fact that Washington raised it at all signals just how seriously U.S. officials are now taking the possibility that China's domestic EUV knowledge, wherever it originated, might translate into either indigenous production capability or unauthorized access to the real thing. The episode also illustrated just how difficult verification has become in a supply chain that's globally distributed and technically opaque. Even a company with ASML's level of internal tracking discipline found itself needing to publicly defend, machine by machine, exactly where every unit it has ever built currently sits, simply to counter a single unverified allegation from within its own government's own trading partner. It's worth stepping back to ask how China's leading effort actually compares, in concrete technical terms, to where ASML itself once stood, because that comparison offers a far more useful gauge of the real timeline than either triumphant Chinese state media coverage or dismissive Western commentary. One detailed technical forecast, built by comparing the reported specifications of China's prototype against ASML's own historical development milestones, places the current Chinese EUV effort at roughly the technical maturity ASML had achieved around 2006 to 2008, years before the company's first commercially deployed EUV systems, and well over a decade before EUV lithography became central to mainstream high-volume chip manufacturing. Applying the same 12 to 14-year gap that separated ASML's demonstration stage tools from TSMC's first commercial 5-nanometer EUV production in 2020 suggests a plausible window for Chinese commercial EUV output somewhere between 2037 and 2039, considerably later than the more optimistic 2028 to 2030 targets circulating in some Chinese industry commentary, though considerably sooner than the essentially never framing implicit in some of ASML's earlier public statements. None of this exists in a vacuum separate from the broader technology Cold War playing out simultaneously on the American side of the Pacific. Even as China pushes forward with the Shenzhen LDP prototype and the longer-shot SSMB accelerator program, American companies and the U.S. government have been placing their own bets on alternative EUV light sources, specifically to reduce dependence on ASML's Dutch-controlled monopoly. A startup called X-Light, backed by former Intel CEO Pat Gelsinger as executive chairman, is developing a free electron laser approach that uses a large particle accelerator rather than tin droplets to generate EUV light. a technology that received $150 million in proposed federal incentives from the Department of Commerce under the CHIPS and Science Act, with Secretary Howard Lutnick specifically framing the investment around reclaiming the frontier of advanced lithography that the U.S., in his words, had for too long ceded to others. X-Light is building its first prototype system at the Albany Nanotech Complex in New York, targeting wavelengths as precise as 2 nanometers, considerably finer than ASML's current 13, 5 nanometer standard, with Gelsinger suggesting the underlying technology could eventually boost wafer processing efficiency by 30 to 40% if it reaches production scale. X-Light isn't alone on the American side either. A San Francisco-based startup called Substrate has developed a competing approach using a particle accelerator to generate even shorter wavelength X-ray light, with ambitions that extend beyond simply challenging ASML. The company has stated its ultimate goal includes building its own fabrication facilities and offering foundry services directly, positioning itself as a potential future rival, not just to ASML's tools, but to chip manufacturing giant TSMC's role in producing the world's most advanced processors. A third American venture, Tau Systems, is pursuing yet another accelerator-based method using laser Wakefield acceleration, firing ultra-short laser pulses into plasma to generate a powerful electric field capable of accelerating electrons across just a few millimeters before producing coherent X-ray radiation through a compact free electron laser setup. And in a development that generated its own wave of attention in August 2026, Elon Musk publicly signaled interest in free electron laser lithography as a technology path for his chip venture Terafab, responding to a social media post claiming the approach was confirmed and insanely bullish, with a characteristically terse endorsement, FELFTW. Japan has entered the same race from a different angle entirely, drawing on its own long history in accelerator physics. Researchers at KEK, Japan's high-energy accelerator research organization, are exploring an approach based on energy recovery LINIC technology, a design that reuses the energy from decelerating electrons rather than discarding it, potentially offering efficiency advantages over both ASML's tin plasma system and the American free electron laser startups pursuing a more conventional accelerator architecture. Japan's involvement matters for reasons beyond the specific technology. The country is home to several of the specialized material and component suppliers that feed into ASML's own supply chain, giving Japanese researchers and companies a uniquely detailed, insider-level understanding of exactly where the existing tin plasma approach's engineering limitations sit, and consequently, where an accelerator-based alternative might offer the most meaningful improvement. None of these efforts, American, Japanese, or Chinese, have yet produced a commercially deployed alternative to ASML's tin droplet system. But their sheer number and geographic spread signal something the semiconductor industry hasn't seen in over 2 decades, a genuine multi-front belief shared across several of the world's most technologically sophisticated economies that ASML's specific engineering approach is no longer the only physically plausible way to generate the light modern chipmaking depends on. Taken together, these parallel efforts, Chinese LDP and SSMB programs on one side, American free electron laser and X-ray startups on the other, paint a picture considerably more complicated than a simple 2-country race to replicate ASML's exact machine. Nobody outside the Netherlands is trying to build tin droplet laser-produced plasma systems from scratch. That specific 30-year, tens of billions of dollars engineering path belongs to ASML alone, protected by decades of accumulated patents, supplier relationships, and manufacturing knowledge that would be almost impossible to replicate, even with unlimited funding and complete freedom from export restrictions. What's actually happening globally is a race to find an entirely different physical mechanism for producing the same 13, 5 nanometer light, or, in the American startup's case, potentially even shorter wavelengths, that sidesteps ASML's specific engineering moat rather than attempting to cross it head-on. China's Shenzhen prototype represents the most institutionally confirmed, most technically concrete example of that alternative path strategy currently in existence anywhere in the world, which is exactly why its validation in December 2025 registered as such a significant milestone, even set against its still substantial remaining gap to true commercial viability. The strategic stakes behind all of this go well beyond bragging rights over who can etch the smallest transistor. Advanced chips manufactured using EUV lithography underpin nearly every frontier AI system currently being trained and deployed, from large language models to autonomous weapons targeting systems to the data center infrastructure powering cloud computing globally. Export controls restricting China's access to ASML's machines have functioned for years as one of the primary tools Washington has used to slow China's ability to independently develop and deploy cutting-edge AI capability at scale, on the theory that without the most advanced chips, Chinese AI development would remain permanently a step behind. The export control regime itself has a longer, more tangled history than most coverage of the current standoff acknowledges, and understanding that history helps explain why the Shenzhen prototype landed with such force. The Netherlands only began restricting ASML's EUV exports to China at Washington's direct urging, a decision that required years of diplomatic pressure precisely because the Dutch government initially had significant reservations about sacrificing one of its most commercially valuable export relationships for the sake of American strategic objectives. China chip conflict as an exercise driven by ideology rather than sound industrial policy, while acknowledging he had to walk a genuine diplomatic tightrope, lobbying Western governments against the tightest possible restrictions, while simultaneously working to protect ASML's intellectual property from Chinese efforts to acquire it through other means. For anyone trying to track where the story goes next, a handful of concrete markers are worth watching, rather than relying on the next viral headline. Whether the Shenzhen prototype's power output climbs meaningfully beyond its current 100 to 150 watt range over the coming year will be the clearest technical signal of real progress, since that single figure drives almost every downstream question about commercial viability. Any formal announcement from SMIC or another major Chinese foundry about integrating the prototype into an actual production line, rather than continued standalone testing, would mark a far more significant milestone than the initial validation itself. And on the American and Allied side, watch whether X-Light, Substrate, or Tau systems produce their first working EUV or X-ray light demonstrations at anything approaching commercial power levels, since a credible non-Chinese alternative to ASML's approach would reshape the competitive picture just as significantly as further Chinese progress would. Until then, what changed in December 2025 wasn't that China caught up to ASML. It's that the question of whether China ever could stop being a hypothetical one. But it is also, by every available technical metric, years, if not over a decade away from matching the power output, reliability, and manufacturing yield that define ASML's current commercial systems, let alone the more advanced high-NA EUV machines ASML has already begun shipping to its existing customers. The gap between producing usable EUV light in a controlled prototype setting and reliably printing millions of defect-free chips on a production line, day after day, for years without significant downtime, remains the single hardest problem in this entire technological domain. The exact problem that consumed 3 decades and tens of billions of ASML's own dollars to solve, and one that raw engineering talent, however skilled, cannot simply purchase or shortcut its way past. What the Shenzhen milestone does prove, regardless of how the remaining technical gap eventually closes, is that the foundational assumption underpinning years of Western export control strategy, that EUV lithography was simply too difficult for anyone outside ASML's specific accumulated expertise to replicate within any relevant strategic time frame, was never as airtight as it sounded from the outside. A monopoly built on one specific 30-year engineering path only remains unbreakable for as long as that path stays the only road anyone is willing or able to travel.